Mic check. Okay. The old one. The new ones is this is just typical workshop.
The NIPS 2016 tutorial is pretty good.
Yeah. It was also simulcast.
Yeah.
All right, good morning, everyone. Welcome to the invited talk of this morning. I'm Fei Sha from University of Southern California. I'll be the program co-chair for the AAAI next year in New York. This morning, I will be hosting and chairing this session. With that, it's my great pleasure to introduce our speaker, Dr. Ian Goodfellow. Ian is a research scientist at Google AI Research. He has made numerous contributions to the field of machine learning. In addition to be the co-author of the deep learning textbook, he's also known as the inventor of generative adversarial network, i.e. GANs. GANs is implicitly defined generative models that has been widely used for generating high-fidelity image, text, and many other data samples. Besides that, Ian also introduced the concept of adversarial machine learning by demonstrating AI's vulnerability to adversarial samples. I think today, if I'm guessing, he's going to tell a bit more details along this very exciting line of work. Now, without further ado, let's welcome Dr. Ian Goodfellow.
Good morning, everyone. Thank you for coming, and welcome to this day of AAAI. I'm here to tell you all about adversarial machine learning and how it relates to very many different research topics that I think many of us are working on here. Most traditional machine learning algorithms are based on optimization. This is where we have a cost function, and we adapt parameters to minimize that cost function. I've shown this here with a 3D plot. The horizontal axes show different parameters, and the blue mesh shows the surface of the cost function. The black trajectory of dots shows how an optimization algorithm can iteratively approach the minimum of this cost function. This works very well for things like classifiers, where we can write down the cross-entropy between the true labels and the predicted labels. And we can just gradually minimize that cross-entropy until we get a classifier that has lower and lower cost. But there are many machine learning problems where it isn't necessarily natural to pose the learning problem as an optimization problem. In those cases, it turns out we can fall back to a slightly harder problem, which is learning within a game. In a game, each player has their own cost, and we are seeking a point that is simultaneously a minimum for each player's cost. The simplest version of this game is what's called a minimax game, in which the cost for player 2 is the negative of the cost for player 1. In this case, we can summarize the whole game with one value function. Player 1 wants to minimize it, and player 2 wants to maximize it. The equilibrium of a game is a point where, with respect to the point of view of player 1, it appears that we're at a global minimum, as shown in the left. And from the point of view of player 2, it looks as if we're at a maximum, as shown in the middle. Each of these two slides on the left and the middle is showing you a cross-section of the value function. The first one is a cross-section through the value function in terms of player 1's parameters, and the second one is a cross-section in terms of player 2's parameters. Finally, let's look at how it looks in 3 dimensions on the right. We see a shape that looks like a saddle, and we see a trajectory of points approaching the center of that saddle, where we have a point that is in one cross-section a minimum and in one cross-section a maximum. This is an equilibrium point where neither player can improve their cost without somehow or other controlling the other player. It turns out that many machine learning problems that are difficult to specify in terms of optimization can be straightforwardly specified in terms of games. It's harder to find the equilibrium of a game, but in many cases, it's worth it for being able to more flexibly specify what we'd like to happen. I'll be walking you through several different research topics that are all important directions for artificial intelligence today. One thing that really interests me is this idea that today, in 2019, most of us are working on different things. It's very different from when I first started working in this field. maybe back in about 2007 or so, when I started working on artificial intelligence research, most machine learning researchers who were interested in AI problems basically all had the same goal, which was to get machine learning to work for AI-level problems. Some of us were working on vision, and some of us were working on NLP, some of us were working on motion planning, but really all of us just wanted to get machine learning to work for these kinds of human-like problems. We already had machine learning working for some things like ad prediction, where it is not necessarily quite AI level, and small improvements in predictive accuracy could be profitable. But until about 2012, most of us were just trying to get object recognition, speech recognition, and so on to work. After the deep learning revolution began with the ImageNet contest victory, we've started to see that deep learning, in particular the supervised form with large labeled data sets, is able to solve many of these problems. Because that first piece of working AI machine learning technology is here, we've now had this Cambrian explosion where people have branched off to study many different topics. I think it's helpful to have a high-level view and see how some of the same ideas are actually impacting all of these different fields. So I'll be telling you about adversarial machine learning and how I see it affecting many of the different new directions in this Cambrian explosion. The first topic I'll cover is generative modeling. The basic idea behind generative modeling is to take a collection of samples, such as the Celeb A dataset with photos of celebrities, as shown on the left, and learn a model that can infer the distribution that generated these samples. Some generative models aim to estimate the density function, others aim to generate new samples that come from the same distribution, and some do both. I'll be focusing on sample generation today, because that's where adversarial machine learning has been most useful. The photos on the right are photos of people who have never existed. They were created by a generative model that was fit to the training data shown on the left. It was possible to accomplish this using adversarial machine learning, in particular using a game between two networks called generative adversarial networks. The first player in this game is called a discriminator, and it's a binary classifier, very similar to the same kind of classifiers we use for object recognition. We train it to look at real data, in other words, samples coming from the training data, and say that this data is real rather than fake. We also train it to look at data coming from the generative model and say that this data is fake rather than real. Thus far, training the discriminator looks just like training a regular binary classifier. We also train a second model, the generator, which actually produces these fake samples, such as the strange image of the cow on the right side of the slide. The generator works by starting with uniform random noise or Gaussian random noise, anything with relatively little structure, and running it through a deep neural network that provides a nonlinear but parameterized transformation. The output of that neural network is then intended to be a recognizable image. Initially, it will just look like noise, but as we adapt the parameters, we eventually get things that look like the cow, and then later we get things that actually look like valid data. The reason that this is an adversarial minimax game is that the generator and the discriminator are competing over the labels that the discriminator should output on the fake data. The discriminator is trained to correctly recognize that the fake data is fake, while the generator is trained to produce fake samples that the discriminator believes are real. The gradient on the parameters of the discriminator helps it to be more accurate, and the gradient on the parameters of the generator from that same cost function help it to steer its outputs toward regions where the discriminator will be fooled. Since the introduction of this framework, it has improved rapidly. Back in about 2014, we have grayscale, low resolution, kind of blurry faces produced by my colleague Bing Xu. And at the right side of the slide, in 2018, toward the end of the year, we have very high quality, high resolution photos produced by a team of researchers at NVIDIA. In between, we've seen rapid progress year over year. One thing that it's not immediately obvious from looking at this slide is that actually the resolution is changing even more than I can show you here. The image on the left is scaled up to make it visible on the slide. The image on the right is scaled down quite a lot to make it fit on the slide. So we've seen rapid progress both in terms of the scale and in terms of the quality of these models. Faces are somewhat easy because there's really only one category of object. Every object is a face. And also our face data sets tend to mostly consist of people looking straight into the camera, and many of them have been registered in terms of putting the nose and eyes and other landmarks in consistent locations across all the different photos. It's been somewhat harder to get generative models to work on diverse data sets like ImageNet, which has 1,000 different object categories. But over the last 2 years, we've seen rapid progress. Augustus Odina began the process of using class conditional models, where you ask the model to generate an example from a specific class. That was the first generative adversarial network that was able to produce recognizable examples of all the ImageNet classes, shown in the top row of this grid. Many of those examples were low quality, even though you could recognize which class they came from. Over the next few years, we saw rapid improvement in the quality of these images, until in 2018 they became realistic, and then later in 2018 they became very high resolution, as well as photorealistic. One aspect of generative adversarial nets that's particularly exciting is that they don't just solve the generative modeling problem, they also solve what's called the unsupervised translation problem. Usually when we use the word translation, we're referring to translating between two different natural languages, such as translating from English to French. We have a sentence that means the same thing in both languages, but can be rendered with a different set of vocabulary and grammar rules. In this context, we're using the word translation somewhat metaphorically. We're saying that we want to take a piece of data from one domain and convert it into an equivalent piece of data in another domain. The example here is converting photos in the daytime to photos at nighttime. The way that GANs are useful for this problem is that they actually make it possible to learn this conversion without pairs of examples from the two domains. Usually when we learn to translate from English to French, we need to take something like parliamentary proceedings, where we have a data set showing us an individual English sentence and a corresponding French sentence. Doing that for things like the day-to-night photo problem would be very difficult. Imagine finding one of the cars on the road that we can see in the day scene, and then trying to track down that car and drive it back to exactly the same position at night. It wouldn't really be feasible to gather these kinds of corresponding pairs. What GANs enable us to do is train on collections of day images and collections of night images without corresponding pairs between them. The basic idea is that the generator learns to convert a day image into a plausible or realistic night image. Instead of having direct supervision in terms of saying that each input belongs with one specific output, we have supervision in terms of the discriminator assessing whether each conversion is appropriate and realistic. One of my favorite examples of this unsupervised domain translation is CycleGAN. Here we see it turning a horse into a zebra. It can do a lot of other fun things like turning apples into oranges. I like the zebra example because it really shows off both how impressive the model is, but also some of the flaws, and it helps to give us some intuitions for things that are problems throughout machine learning. One well-known problem throughout machine learning is that there can be biases in the data set that affect what the model learns. You can actually see that really clearly here. Horses tend to be photographed in more green environments, and zebras tend to be photographed in more yellowish, dry environments. The model here doesn't actually know that what we really care about is the horse, so it's actually converting everything. It makes the background look more like a background where you'd see a zebra, as well as converting the foreground from a horse to a zebra. One other thing we can see from this slide is that the video is generated one frame at a time. The GAN here has been trained to convert individual photos of horses to individual photos of zebras. It doesn't actually know that we're using it to make a video by stitching those frames together afterward. And that means we can see some glitches in the video. One of the biggest glitches is if you watch right when the horse turns, the stripes on the zebra remain in place and his head moves across right there. So one way that we can actually improve the quality of video is to explicitly model the videos and make a discriminator that assesses whether a whole video is realistic. That means that the discriminator can look at successive frames and make sure that the motion is smooth. So this project from NVIDIA shows how a video-to-video synthesis model can convert line drawings of faces and take the animated line drawing and turn it into a photo of a face. It's actually generating the whole video in a single chunk of data, so it looks for a realistic motion as well as realistic appearance. It's also a multimodal model, meaning that it can generate multiple output samples for each input sample. So this line drawing can be converted into multiple different people. It's also possible to take 3D models of people dancing and render them into realistic photos of people dancing. So we have the 3D model as input, and we have the person in photo quality as output here. In this particular project, we're starting with a 3D model and then going to an output video. It's also possible to start with an input video of one person dancing and convert it into a video of another person dancing, as demonstrated in this project from Berkeley called Everybody Dance Now.
Lobster tail for dinner. Julio served that scampi. You got it if you want it. Got it if you want it. Said you got it if you want it. Take my wallet if you want it now. Jump in the Cadillac. Girl, let's put some miles on it. Anything funky for you, that's what I like, that's what I like.
I personally am really glad that I never had to dance for any of my grad school projects. I find it kind of fun watching the YouTube videos, watching the faces of the grad students in the demonstration videos. Some of them look a little bit concerned while they're doing the dance. All right, so far I've mostly shown you things like videos and images. Generating digital effects like videos and images is really important if you work at a company like Adobe, where you're making effects software, or if you work for an effects studio making realistic videos for TV or for feature films. It's also interesting for gaming companies. But I think actually probably most of us here are not working in those particular industries. So I'm really excited to see that GANs are actually starting to move out into the real world. One of the first physical applications of GANs that I know of is a company called Glidewell Dentistry has produced a generative model of dental crowns. So a dental crown is like a replacement top to your tooth if you have to have the tooth partially removed. Traditionally, the dental crown is designed by a human technician. It's actually a difficult process. It needs to be personalized for each patient. When the patient closes their mouth, the dental crown needs to fit the shape of their other teeth. It can't just be flat or square or something like that. And it also is a functional object. It needs to be able to successfully bite and chew and actually cut food apart when you need to eat. Usually a dental crown is first installed with a temporary crown. When the patient first comes in and has their original tooth removed, they get a relatively low quality impersonal crown installed, and then about 2 weeks later they get the custom-made crown installed. So it actually takes 2 different operations to get the final result. Using this new GAN-based approach, it's possible to generate the design of the new crown right away and 3D print it on site, so you only need 1 operation to install it. I'm hoping that we'll actually start to see generative models designing more physical objects and designing other useful systems over the years ahead. One area I've been predicting would be transformed by generative models soon is fashion, where I think it should be possible to generate clothing that fits individual people really well, and also to build models of different people's tastes. So how do all these models work? What are some of the ingredients of the latest state-of-the-art results? One thing that we found is really important in my group at Google is self-attention. By self-attention, we're referring to a paper from Facebook AI research called non-local neural networks. And it's essentially an attention mechanism where you can add it to a convolutional neural network, and when you generate each location in the feature map, you can actually use an attention mechanism to focus on other parts of the previous layer's feature map. We can walk through how that's useful a little bit here by looking at the dog in the upper left. If you look at the red point on the dog's eye, we're now going to make a feature map showing us where the attention is focused when we generate that particular pixel of the dog. So right next to it, we have this black and white map of where the attention is, with some arrows indicating how the attention is spread. We can see that the attention for generating the dog's right eye is mostly focused in the area of the eye and also the dog's left eye. We believe that what's going on is that this helps to make sure that the dog ends up with exactly 2 eyes and that they're symmetrical, that they're the same size and color and so on. Before the introduction of self-attention to GANs, we tended to have these problems where convolutional networks would generate multiple copies of body parts. So you might get something like a really cute puppy that has 3 really cute puppy heads stacked on top of each other. It didn't really look very realistic, but convolutional nets without these attention mechanisms are so good at sharing weights across different locations that they tend to care whether a feature is absent or present, rather than knowing how many of them there are, or knowing that they're in the right location. As we look at some of the other images, we see the dog on the right, and we look at the blue dot, where as we generate the dog's leg, the attention map looks around both at the leg itself and at the neighboring leg. I think this helps to get the 3D perspective right, and also to make sure that the dog has legs at all. With previous convolutional networks, it was very common for GANs to draw dogs with no legs. I think what was going on there is that there was no way to coordinate between different locations in the feature map. All the different locations had the same parameters. And I think each location tended to make a bet, most of the pixels on the dog aren't legs, so the probability of me being the legs is very low. Now that the attention mechanism allows global coordination, we make sure that some of the pixels actually realizing they're the ones that are responsible for drawing the legs. I've also been really impressed with how well these attention masks work. One thing that I like about them is that they're not constrained to something like a circular attention region or a square attention region. If you look at the tail of the bird at the bottom of the slide, we actually find that the attention mask for drawing the tail is a very elongated diagonal region. And that flexibility has just been really nice. In the last few months of 2018, we saw two really big advances in the quality of GANs. One of them is the paper that's been colloquially termed Big GAN by Andrew Brock and collaborators at DeepMind. It's a large-scale TPU implementation of GANs. It's pretty similar to the self-attention GAN model that we saw in the previous slide, but scaled up quite a lot, and with some new techniques introduced that are important for successful learning at that scale. It successfully generates images like this dog with white fur that are good enough to fool human observers, and actually quite high resolution, up to 512 by 512 pixels. Most previous results on ImageNet were only 128 by 128 pixels. For other generation tasks like generating faces, there's a really high quality new generator called the style-based generator. It's particularly exciting because it allows us to separate different factors that are involved in controlling the appearance of the final sample, and we can then control them separately from each other. For faces, there's a model that separates the faces into coarse style, medium style, and fine style, where fine style is details like where individual hairs or wrinkles are placed on the face, and coarse style is more of things like age and sex. So all three of the faces I'm showing you here are generated faces. None of them are training data, none of them are photos of real people. And I am demonstrating here how the style transfer mechanism works. So let's say that we have a point in latent space represented by the person on the left, and we want to transfer the coarse style of the person in the middle onto this face. One of the most salient things about the person in the middle is that they're a child, so we actually get a child version of the person on the left. So again, all three of these images are generated. They are represented by different latent vectors describing the coarse style, medium style, and fine style of each face. What we've done is we've shown what happens when we change the encoding for just the coarse style. Overall, this makes it possible to do much more controllable generation and also gets really high quality, high resolution results. So far we've covered generative models. Another branch of our Cambrian explosion of new research directions is actually how do we make machine learning secure? Until recently, machine learning just didn't work at all. It was broken with no one attacking it. Now that it's starting to work and be used for important things, we'd like to figure out how to make it work when it's under attack. Unfortunately, it turns out that when you attack a machine learning model, it's very easy to fool it. One of the main kinds of security problems we face is unusual data at test time. One of the kinds of problems that we face is called adversarial examples that I've demonstrated here. The image on the left is a photo of a panda that is successfully recognized with 58% confidence as being a panda. If we blend in just a little tiny amount of the image in the center of the slide, it is then recognized with 99% confidence as being a gibbon. So we've not only made the model make a mistake, it's actually more confident about the mistake than it was about the original correct prediction. If an attacker wanted to make a machine learning model produce an output of the attacker's choice, that could actually be a serious security concern if the model is used for something important or dangerous. In general, we think that these adversarial examples are a consequence of moving away from IID data. Most of the time when we design machine learning models, we assume that each of the data points is generated independently from the others. And we also assume that the test distribution is the same as the training distribution. Attackers can violate both of those assumptions. For one thing, they can show us unusual data that doesn't come from the same distribution as we saw at training time. They can add graffiti to stop signs and make them misrecognized as not being stop signs anymore. Or they can just take relatively normal real-world data but find ways of presenting it that aren't standard in the training set. For example, I took this photo of an apple in a mesh bag, and it's no longer recognized as an apple. So those are relatively simple, non-exotic steps away from IID data that are enough to fool models. It's also important that we are violating the independence assumption when there's an attacker. Usually we think that each training example and each test example are generated separately from each other. But an attacker can generate highly correlated examples when attacking a model. In fact, they don't even need to violate the identical assumption, they can actually just use the normal distribution that we have at test time, find a single mistake, and then repeat that example over and over again, which is kind of maximally non-independent because all the new attack examples are the same, but it accomplishes the attacker's goal of fooling the model on every input. These adversarial examples work in the physical world. You don't need to have direct access to the model's input. You don't even need to do very much to successfully fool the model in the physical world. We showed that you can actually make an adversarial example, print it out, and then take a photo of it with a phone, and it will still be misrecognized. There's a lot of other work on how to enhance the adversarial examples so that they work from multiple distances and viewing angles. You can even 3D print objects that are adversarial examples. All of this is related to the idea of adversarial machine learning because we can think of this as a minimax problem. The defender, the person building the classifier that we want to work correctly, is searching over parameters to find the parameters that reduce the cost incurred by the classifier as much as possible. And simultaneously, the attacker is searching over the inputs to the model that maximize the cost incurred by the defender. In particular, we can actually try to do better as a defender by playing this minimax game explicitly and running gradient descent in the outer loop on the parameters, while the attacker runs gradient ascent in the inner loop on the inputs. Here we can compare what happens when we train two different models, one using adversarial training and one using regular training, and we evaluate the model in terms of its accuracy on adversarial examples and on clean examples. The first curve to look at here is the blue curve. It's an error rate shown in log scale, and it starts off high and then eventually drops to be low and levels off. That's when we train on clean examples and evaluate on clean examples. It's just the regular kind of learning curve that we're all used to looking at. The next learning curve to look at is the green curve that stays near the top of the plot across the entire plot. This is what happens when we train on clean examples and evaluate on adversarial examples. The error rate stays high throughout the entire course of training. So training on just clean examples doesn't really do much of anything for adversarial robustness. And then the next curve to look at is the cyan curve. That starts off high and then decreases over time. It doesn't get quite as low as the dark blue curve, but it does get down to much smaller than the starting value. This cyan curve is what happens when we train on adversarial examples and evaluate on adversarial examples. By training on adversarial examples, we're able to become somewhat robust to them. This is still a research direction, and it isn't actually good enough to use for security and real-world purposes, but it's one of the best approaches that we've got so far for improving security and research benchmarks. Another thing that's particularly exciting about adversarial training is that sometimes it actually makes the original model better at the original task. If you look at the red curve here, we see that it starts off high and actually drops to a lower error rate than the blue curve. So by training on adversarial examples, we've actually gotten better accuracy than training on clean examples when we test on clean examples. This turns out not to be the most common outcome. When you have a large labeled data set, a lot of the time there's a trade-off between accuracy on clean examples and adversarial examples. But there are a few settings where adversarial training helps with accuracy on clean test examples. It comes up most often when you have a limited amount of labeled data, and we'll revisit that idea later on. So some of our Cambrian explosion of machine learning research topics is about adding nice properties to models that already work, like adding security to classifiers. Another direction in our Cambrian explosion of research topics is to enable totally new capabilities for machine learning algorithms, to make machine learning useful for things that it can't really do yet. One domain that I'm really excited about is model-based optimization. Model-based optimization is where we train a machine learning model, and instead of just using it to label new data, we actually use it to guide the search for better data points. So imagine, for example, that we have a model that predicts how fast a particular design of car will be if we go ahead and build the car. You can imagine training it on different things like the Model T or like a modern sedan. And then after we have this model that predicts how fast different designs will be, we can start to optimize for faster and faster cars, extrapolating off to the right side of the slide, getting extremely fast cars. Unfortunately, if we do this today for quite a lot of different data domains, instead of getting a really good car design, we will actually get an adversarial example that the model thinks should be a really good car. So this is an open research area where it's tightly related to the adversarial training research directions. You can think of this as very similar to making a model that's robust to adversarial examples. We want the model-based optimization search procedure to find points that are truly good instead of fooling the model into thinking they're good. It also looks a lot like a GAN. You can think of the GAN as model-based optimization of the real rather than fake function. But there's a lot of other unobservable functions that we can learn and indirectly optimize. I'm excited to see things like model-based optimization for design of faster chips, design of more energy efficient systems, and also design of better genes. One way that we can produce useful medicines is actually to design DNA sequences that cells will turn into proteins for us, and then we can harvest those proteins and use them for medicinal applications. In order to do that, we need to be able to design good DNA sequences that have strong medicinal effects by binding to the receptors we want them to bind to, and also have a low number of side effects by not binding to the receptors we don't want them to bind to. There have been a few different papers on early work using generative adversarial networks to actually produce high-quality proteins in a few different simulated contexts. And I'm excited to think that this might actually make the jump to the real world and start being used for real therapies in the near future. I think everyone knows that reinforcement learning is a really hot research topic today. I think one thing that people don't think about there quite as much is how adversarial machine learning is relevant to that topic. First off, it's also possible to make adversarial examples for RL. Sandy Huang at Berkeley showed that you can make adversarial examples that fool machine learning policies into performing worse on games like Atari, like Sequest shown here. Small changes to individual pixels are enough to actually degrade the agent's performance. Other researchers have later shown things like you can control an RL agent and make it navigate to a state of your choice, so you can actually get really specific, flexible control of the agent. But another way that adversarial machine learning is related to reinforcement learning is that reinforcement learning and adversarial machine learning are some of the oldest kinds of machine learning, period. Back in the 1950s, one of the first really important machine learning results was Arthur Samuel's checkers playing agent. It really helps to dispel a common misconception. The common misconception is that a computer can only do what it is programmed to do, and therefore it can only do things that the programmer knows how to do. As most of us are aware today, the reason this is a misconception is you can program a computer to learn, and then it can go ahead and learn things that the programmer didn't know how to do. The checkers playing agent that Arthur Samuel built worked via the self-play process. It would play games of checkers against copies of itself and learn from those games until it became able to play checkers better than Arthur Samuel himself was able to do. That same principle is still alive and well. We see it in things like AlphaGo and AlphaZero, and also in OpenAI's Defense of the Ancients bot that is able to beat several human pros. We've also seen it in things like the sumo wrestling project from OpenAI, where sumo wrestling agents learn to do things like fake out their opponent with incorrect telegraphed moves. And they learn that all from self-play without needing any kind of supervision signal to say that deception is something useful you might want to use in a sumo wrestling game. Another way that adversarial machine learning has been useful for reinforcement learning is providing learned reward functions. We see this kind of example in a project called Spiral, which stands for Synthesizing Programs for Images Using Reinforced Adversarial Learning. The basic idea of Spiral is that we want to convey a goal state to the model in a formula where we can't actually reach the goal state perfectly. So for example, if we want the robot to paint this handwritten character, it's from a language captured on omniglot.com. The robot will actually look at its canvas through a camera, and the pixels coming out of that camera in the real world are never going to look exactly like the pixels in the bitmap that we provide as input to specify the goal state. The bitmap that we use to specify the goal state is really perfect with absolutely black ink and absolutely white background canvas, and there's also no perspective transformation or anything like that. The robot is actually going to view the canvas at a camera angle that isn't quite head-on, and there's things like shadows and lighting effects on the canvas. It turns out that if you just use mean squared error to try to approach this goal state, the robot can't learn to do it. But if you use something like a GAN discriminator to learn to measure distance from the goal, it can actually provide a useful distance measure that makes it possible for the robot to learn to accomplish this goal state. So adversarial learning has turned out to be a useful alternative to handcrafted reward functions. One research area that I'm very interested in is extreme reliability. We have machine learning models that work well enough to work in low-stakes situation, but a lot of the reason we want to build AI is to replace error-prone humans in very dangerous situations and make those dangerous situations safer. We'd like to have things like autonomous vehicles that essentially never crash. air traffic control systems where we don't need to worry about a human being tired and making a mistake. We'd like to have things like surgery robots, with essentially arbitrarily steady hands that never make a mistake. So far, machine learning is actually relatively error-prone. It's somewhat easy to get to low error rates where we're happy to have the machine learning model recognize speech when we ask it to navigate to different locations. It's not the end of the world if it doesn't hear our sentence correctly. We're happy to have machine learning organize our photo albums. But we're not quite at the point where we'd want to take an RL algorithm and have it learn to use a scalpel. One of the reasons that I'm interested in adversarial machine learning is that I believe it will help us to produce extremely reliable systems. We see how the idea of worst case analysis has been useful in other engineering disciplines. If you think about, for example, distributed systems for traditional computer science, we want to have multiple machines connected on a network, implement a large-scale file system like we use to store all of the data we use at Google. It's actually a relatively difficult engineering problem. Multiple computers communicating over the network are prone to errors like a machine crashing and not being able to report that it has crashed. Machines can also randomly drop packets and sometimes send packets in error. So how have we actually overcome this chaotic problem of many different machines having randomized errors? It turns out that the work that was done to solve this problem was based on assuming that some of the machines were controlled by a malicious adversary who chooses to actually take the worst possible actions in each setting. So if you assume that an adversary will intentionally crash the machine at the worst possible moment, or will drop the worst possible packet, or will send the worst possible fake packet, and an algorithm can be designed that runs on all of the remaining machines that are not controlled by the adversary. If that algorithm can be proved to work even when there are malicious machines trying to interfere with it, it turns out that it's guaranteed to work really well in the real world. I think we'll see that same principle applied to machine learning algorithms. And we're already starting to see some of the tools that we use for adversarial machine learning having an impact on these extreme reliability situations in real life. One example is that there's been a lot of work on verification systems for proving that machine learning models have no adversarial examples in some specific region. One of these systems called ReluPlex can actually be applied to air traffic control systems to verify that they implement the correct procedure. Another research direction in our Cambrian explosion of machine learning research is label efficiency. Today, most applications that we'd like to solve with supervised learning are solvable if we have a very large labeled data set. But it's relatively common to lack either a large data set or to lack labels for it. In the case where we have a large data set but we don't have labels, an interesting direction is semi-supervised learning, where we try to learn from both labeled and unlabeled data. There are two different ways that adversarial machine learning has been useful for semi-supervised learning. One of the first of these that we saw emerge really effectively was actually using GANs for semi-supervised learning. The way that this works is to focus on the discriminator rather than the generator. Usually when we train a GAN, we actually just throw away the discriminator at the end of the day. It's useful for guiding the learning process, but isn't really used for generating the data after we've trained the generator. In the context of semi-supervised learning, we're actually upgrading the discriminator to be a multi-class classifier. And at the end of the training process, the classifier is the thing that we're interested in keeping around. For a traditional GAN, the discriminator is a two-class classifier. It says whether the input is in category 1, real things, or category 2, fake things. For semi-supervised learning, if we'd like to learn an n-class classifier, we make a GAN with an n+1 class discriminator. So suppose that we'd like to learn to classify two classes, cats and dogs. We can make a classifier that has 3 different classes. 1, the class of real cats. 2, the class of real dogs. And 3, the class of fake things. When we train this system, it actually gets to learn on 3 different kinds of data. On real labeled data, we can actually just tell it to maximize the probability of the correct label. So if we have a photo of a cat and it's labeled as a cat, we can actually maximize the probability of the cat class in this discriminator. The second category of data that it gets to learn from is unlabeled real data. So suppose we have a photo. We don't know whether it's a cat or a dog, but it is a real photo. In that context, we train the discriminator to maximize the sum of probabilities over the real classes. And then finally, this model can also learn from fake data. When we generate a sample from the generator, we train the discriminator to classify it as a fake sample. And that means that we actually have 3 different ways of exercising the features learned by this model, and it gets really a lot of experience. Back in 2016, we showed that you could actually train a GAN to recognize all the MNIST digits correctly with less than 1% error, using only 100 labels. To get to that level of error took 60,000 labels just a few years before. Another way that adversarial machine learning is useful for semi-supervised learning is called virtual adversarial training. The idea behind virtual adversarial training is that we don't really have hard constraints on the unlabeled examples. We can make some virtual constraints. So instead of saying this example should be classified specifically as category 1 or category 2, we can do is we can take an unlabeled example and we can say, we don't know what the label of this example is, but we know that it ought to be labeled the same, whether or not an adversary has made some nuisance modifications to the image. So you actually create an adversarial example designed to flip the classifier's prediction for that unlabeled example, and then train the model to produce the same prediction on both the original and the adversarial example. This technique was developed by Takeru Miyato, and in a recent benchmark, we actually found that among several different currently competitive semi-supervised learning results, it's actually the best. In this plot here, we vary the number of labeled examples on the x-axis. On the right side of the plot, where there's quite a lot of labeled examples on the SVHN data set, we find that all the models perform about the same. With a lot of labeled examples, semi-supervised learning isn't really any better than pure supervised learning. But as we move to the left and reduce the number of labeled data points, we see that the error rate really climbs for most of the different semi-supervised learning models that we have here. Virtual adversarial training does have an increase in error as we move down to 250 labeled data points, but it has a much more flat trade-off curve than the other algorithms do. Another way that we can address a lack of data is to use what's called a domain adaptation technique. Domain adaptation is when we train in one domain where data might be abundant, and then we test in a different domain. So what do we mean by domains exactly? You can imagine one context might be training an object recognition algorithm, and one domain might be the domain of clean examples in the ImageNet data set, where everything has been very carefully curated. And another domain might be the domain of photos on users' cell phones, where each photo is taken under relatively active circumstances, walking down a street at night, that kind of thing. Those photos are not nearly as carefully curated and also have different kinds of objects in them. So if we are able to train in one domain and then perform well in a different domain, that can help us with limitations on the amount of labeled data that we have. For example, you generally can't harvest photos from users' cell phones to label it. You can only use some kind of public data set for training. One way that we can assess the performance of domain adaptation algorithms is to use different collections of labeled object detection settings. So for example, there's the Viper and the PRID and the CUHK data sets. They're all pedestrian detection data sets, but they're collected with different cameras in different cities and so on. So they actually work as different domains, and we can see how well we can, for example, train on Viper and test on PRID. One of the main approaches to domain adaptation is called domain adversarial networks, developed by Yaroslav Ganin and collaborators. The basic idea behind domain adversarial networks is to play a game between a feature extractor and a domain recognizer. The feature extractor pulls out features from the input, and the domain recognizer takes those features and tries to guess which domain they came from. For example, it might take features extracted from an image and guess whether they came from the Viper dataset or the PRID dataset. In this game, the feature extractor wants to pull out features that are useful for classifying the input, and also wants to make sure that its features don't give any information to the domain recognizer. And the domain recognizer is just a binary classifier that's trained to correctly recognize the domain. This forces the model to pull out features that are somewhat independent from the domain and causes it to generalize better from one domain to another. An interesting twist on this domain adversarial learning idea is called professor forcing. Professor forcing fixes a problem with drawing samples from recurrent networks. Usually when we train a recurrent network, we use it in what's called teacher forcing mode, where if we're trying to generate a sentence, we actually use the training data to guide the recurrent net on every step of the generation process. So if we have a sequence of words, the recurrent net will predict what the next word is, and then instead of using its prediction, we feed in the actual word from the training data. This means that a lot of the time when you start to run an RNN in free sampling mode, and you actually feed its own predictions back into itself to generate the samples, the new domain of self-sampling sentences is so different from the training domain of teacher-forced real data that the RNN starts to just go further and further off course and generate really unusual things. Professor forcing takes the idea of domain adversarial learning and treats teacher forcing mode and free running mode in the RNN as two different domains. So you use a domain recognizer and try to make the RNN produce the same statistics of sequences of hidden states, regardless of whether it's running clamped to the data or running in free sampling mode. A very important domain adaptation problem is adapting from the domain of synthetic data to the domain of real data. A lot of the time for robotics problems, we would like to train on synthetic data and then use the robot in the real world. One example of this is a project from Apple on training an eye gaze direction detector so that you could actually hold up a phone with a front-facing camera that can see your eyes and tell where on the screen you're looking. So you could click on icons just by looking at them. It's a challenge to get data for this kind of problem because it's hard to tell where people are looking. There are eye tracking machines, but their resolution isn't the greatest. There are ways of improving the resolution of eye tracking machines. In studies with monkeys, sometimes researchers actually embed metal coils on the cornea of the monkey, but we don't usually want to do that to human subjects. So we can get photos of human eyes easily, but not necessarily tell where they're looking. We can also do things like make 3D models of human eyes and render them. Because we control the 3D model, we know where it's looking, but the rendered image turns out to be too different statistically from real photos, and models trained only on 3D rendered images turn out not to work very well in real photos. This is where adversarial learning comes in. We can actually use a GAN to meld these two sources of data. A lot of the time I hear people suggest that maybe we could take a GAN, train it on a data set, and then generate a lot more samples from that same distribution with the hope that it would provide a bigger data set for some other model like a classifier. I haven't actually heard of that working. It seems to me like it requires the GAN to somehow generalize better than the classifier would. But what GANs are useful for is melding different sources of data. Here we have the 3D rendered data where we know where the eyes are looking, but the data isn't realistic enough. And we have the unlabeled real photos where we don't know where the eyes are looking. We can then take a GAN that enhances 3D images with known gaze direction and make them look realistic. So we've melded this data to get both realism and labels. And that's one way that GANs are useful for actually giving us new sources of data, where we aren't expecting them to just increase the number of samples we have, but they're qualitatively transforming what kind of signals we can have in the same place. We've also seen a very similar project at Google called GraspGAN, where we can take a simulated 3D image like the one on the left and convert it into a realistic photo like the one in the middle. This approach is really nice because since we started with a 3D rendering that we control, we can actually get a per pixel label mask on the right just by knowing which pixels were rendered from which object, but we still get photorealism as shown in the middle. GraspGAN turns into better grasping performance for the robot model. For many different amounts of real labeled examples, we can see that there's a blue bar showing what happens if we train with only simulated data, and a red bar showing what happens if we train with only real data. Real data is better than simulated data, but combining simulated and real data is better still. It's useful to do this not just because the final grasping performance is better, but also because using less real data is both faster. You don't need to wait for the robot to actually carry out the grasping in the real world. And it also just costs less in terms of robot maintenance. Robot parts actually wear out when you have the robot grasp again and again and again all day. GANs can even be used to learn robot grasping without real data. A recent paper called Sim to Real via Sim to Sim shows how we can learn a cycle GAN-like model that can convert from many different kinds of images to a canonical simulation image. At training time, the GAN is shown randomized simulation images, like in the upper left, where different aspects of the appearance of the simulator have been randomized by adding unusual textures to the scene. The GAN learns to convert these to a relatively normal-looking canonical simulation, shown on the upper right, and then the agent is trained to grasp when it gets to see images in the canonical view. The learned system can then be deployed in the real world. The GAN sees the real photos coming in and converts them to look like the canonical simulation, and then the agent acts on the canonical simulation. So we have this agent that has only ever really learned to work in simulation, and the GAN is this interface that allows it to bridge the gap between the domain of real images and the domain of simulated images. One very important research topic these days is fairness, accountability, and transparency. Now that machine learning is starting to be used for important decisions that affect people's lives, we really want to understand how it works and make sure that it's being applied fairly. One way that adversarial machine learning is helpful for this is learning fair representations. We've seen how you can use domain recognizers to force feature extractors to learn representations that don't tell you which domain data was extracted from. You can actually use this same idea to ignore particular sensitive variables, such as a person's sex or race. If you just omit sex or race from a description of a person, it's often possible to infer that information. For example, a zip code often can tell you the demographics of a neighborhood of people who live in that zip code, and you can guess with high probability several of their characteristics that we'd prefer to ignore. This fair representation learning process is able to learn a representation that captures many of the task-relevant aspects of a person, but throws out many of the things that we think would be unfair to pay attention to. I also think that adversarial machine learning will be important for interpreting models and understanding what they're actually doing. So far, there's been a large literature on interpretability and a separate large literature on adversarial vulnerability. I think that these two fields should actually talk to each other a little bit more. A lot of the time in interpretability papers, we see very positive results that say essentially the models are working correctly and getting the right answer for the right reason. For example, on the left, we see that one interpretability technique says that this photo of a cat and a dog can be recognized as a cat because specifically of the cat pixels, and it can be recognized as a dog specifically because of the dog face pixels. At the same time, in the adversarial machine learning literature, we usually are finding that most of these models are broken and tend to get the right answers for the wrong reasons and can be easily made to get the wrong answers. So for example, the panda image can be made to not be recognized as a panda anymore without needing to really get rid of any of the panda pixels. So I think that these two literatures should combine a little bit more, and I hope we start to see interpretability tools that expose the flaws in machine learning models and help us to debug them more thoroughly. I also think that if we succeed in making adversarially robust models, those models will be more interpretable. When you have a model that is not adversarially robust, a good explanation of how the model works needs to specify all of the different mistakes it makes, and it can be hard to enumerate all of those. Whereas a model that just gets the right answer most of the time can basically just be described in terms of which task it is correctly carrying out. We've seen an example of this on the MNIST dataset, which is one of the few places where it's easy to actually make a robust model. On the left, I show you what happens when you take a linear model, just a softmax classifier. We often think of linear models as interpretable, but I actually don't think they are. People have very bad intuitions for how linear functions behave in high-dimensional spaces. What I show here is an animation where I start at the upper left with an image of a 9, and I run gradient ascent on the probability of the 0 class. And as we see, reading left to right, top to bottom, like words on the page of a book, we follow the steps of gradient ascent until the first yellow box at the upper right. That yellow box is showing where the model thinks that the input is now a 0 with high probability. And as we continue left to right, top to bottom, each other yellow box is showing where the model thinks it's a 1, a 2, and so on. We actually hit all 10 classes, and the only one that looks correct is the 9 at the bottom right. The only reason that one is correct is that we started the whole process with a 9. So this linear model that you might think of as interpretable has this very counterintuitive failing. At the same time, we can make a robust model on MNIST, shown on the right, and when we run the same process there, we start optimizing for the 0 class, we actually get recognizable 0s, recognizable 1s, and so on. So it actually behaves more according to what a human would expect. I would argue that this makes this model more interpretable, though I recognize I don't really have a definition of interpretability. So that's not something I'm prepared to quantify right now. The very last topic I'm going to cover today is neuroscience. So far, especially deep learning people working in machine learning have drawn inspiration from neuroscience. I think we're now at a point where we can actually start to draw even more inspiration, and also we can start to talk back and have machine learning give insights about neuroscience. One exciting Google Brain Residency project that I served as the mentor for recently involved building adversarial examples that fool both humans and machines. Most of the adversarial examples we made fool only time-limited humans. But we actually found one example that fools humans that have no time limit, as shown on the left. We have this image of a cat, and we can perturb it to look like a dog. To me, it looks very much like a German Shepherd. It's debatable about whether we've actually changed the true class of the image here, though. So there's some philosophical considerations in interpreting it. The pair of images on the right, where we have an image that starts off as a spider, can be perturbed to be misrecognized as a snake by humans who have no time limit, or by humans who have a time limit. Humans who have no time limit tend to agree that it's still a spider, so we don't think that we've accidentally changed the true class of this image. Instead, we've actually found a way of fooling the human visual system under time limits into thinking that it's a snake. This is interesting for machine learning because we know a lot about the differences between the human visual system under a time limit and the human visual system with no time limit. In particular, in the first few milliseconds of processing, the human visual system is all feed-forward and looks a lot like a modern convolutional net. After a few more milliseconds, the human visual system starts to have recurrent top-down updates. And that suggests that maybe some of the robustness of the human visual system comes from these recurrent top-down connections. I think we're really just at the start of this process, though. Now that machine learning basically works, we can find interesting bugs in it and check if the human visual system has the same bugs. I think that will help us to rapidly learn both how to identify mechanisms in the human brain and how to copy some of those mechanisms back to the machine learning models to improve them. Thank you, and I'm available for questions.
So we have a few minutes for questions. Just be mindful, we're going to have a very quick room turnover, so we're going to cut off at 9:45. And if you have questions, please go to the mics on the corridors over here. So, okay.
A while ago, there had been a little bit of controversy about things like deepfakes, where generative models are also adversarially used to attack certain people. Can you comment a little bit on how you think we can mitigate that, and whether adversarial learning would be enough for that, or do we need more than just that?
Yeah, that's an important topic and actually a very complicated topic. I would say that the thing I think would be most helpful for mitigating that is actually changing the culture and educating people so that people understand that they might be seeing a deep fake. The original theorem from the Gann paper about how the generator is eventually able to produce samples that fool the discriminator also seems to apply to the real world. Given infinite resources and infinite time, the game theory suggests that the fakes become good enough that you can't detect them by inspecting them. There are some other technical solutions you could work on, like making cryptographically signed images that you can verify that those images are real. You can do things like analyze who is propagating videos on social media, kind of the same way that we detect email spam by seeing who's sending it. But it seems like it will be really hard in the long run to actually tell whether a piece of media is real or fake just by inspecting it. It could also be it could backfire to have a fake detector that everyone trusts, and then someone finds one fake that fools it, and then people believe it much more than they would if there was no fake detector. So I personally think that the best way to mitigate this is to build like fun, harmless tools where people can make deep fakes of themselves and their friends for fun. You know, like put yourself in a video game or put yourself in a movie you're watching, and get people used to the idea that images should no longer be considered evidence that the thing you're seeing was real, unless they're like cryptographically signed by a trusted authority or something like that. But it's a really hard topic and not something I think I can address in this short of a question period.
Thank you very much for a very comprehensive talk. I noticed that most of your examples were from the domain of vision. I was wondering if you have some thoughts on why we haven't seen similar successes in the field of, let's say, natural language processing. Is it because making a good generator is the problem, or is it something else?
The biggest challenge with natural language processing is that the data is discrete. And so for a GAN, you need to be able to backpropagate from the output of the discriminator back to the parameters of the generator. If the output of the generator is discrete, then you don't get any useful gradient through whatever you use to discretize the output layer. You can imagine using reinforcement learning techniques like policy gradients to train the generator and think of it as a policy generating a sequence of discrete actions. But for NLP, that's also really hard. A lot of the cases where policy gradient works well have relatively low dimensional action spaces, and the action space of a sentence is just gigantic. So far we haven't really found a good way to overcome that problem.
Yes, thanks for the talk. Actually, I have a question about for generative models. So So in real world vision, we actually have this physical world, so we can have very good simulators to generate very realistic things. Another direction is that you can use the generator to fully depends on the deep learning. So how you think which one is better, or you think about combining them together as another better way? So that is also considered about like human brain, if you whether human brain have a physical kind of simulator that we can basically depends on to generate new examples. What's your opinion about that?
I guess this is an area where I have less expertise, but my guess would be that in the short to near term, it's probably a lot better to use hybrid approaches rather than trying to do pure simulation or especially trying to do pure deep learning simulation. Some examples of hybridization I think are pretty cool are things like deep learning super sampling, where you use deep learning to do anti-aliasing of images rendered in a simulator. Or there have been a lot of examples of mods for games where you take an old game and you use GANs to do super resolution on the textures, so that you're still using the rendering engine, but the quality of the texture is boosted a lot. It seems unlikely that we'll have generative models that can compete with the quality of physical simulators without having anything kind of scaffolding them up anytime soon. But in the long run, maybe we will. In the long run, maybe the machine learning model gives us more flexibility than hand-coded rules would give us. And then in terms of the human brain, my suspicion is that we don't really have a full simulator. But I'm not a real neuroscientist, so I don't have a lot to back that up.
Thank you.
I'm sure this is a very exciting topic, and I think you're valuable to discuss offline, but we probably have to get out of the room now. With all the appreciation and thanks, let's thank the speaker again.
Thank you.
So if you could, please evacuate the room as soon as possible, as the staff needs to rearrange the room. Thank you.